Good morning, students. Welcome back to our physics classes. So, during the last two classes, we were discussing about the kinetic theory of gases. And in the last class, we have seen last class we have started with the pressure equation, and from that pressure equation, we have derived the relation between RMS velocity and temperature, RMS velocity and molecular mass, then temperature and kinetic interpretation of temperature. Then we have seen the Cp and Cv for different types of gases, just like monoatomic, triatomic, diatomic and triatomic, in terms of degrees of freedom, then equipartition, theorem of energy. All these matters we were discussing during the last two classes. And nothing else is remaining there in the chapter except two familiar content. Content means two familiar concepts. One is, already we have defined the term, that is mean free path. What do you mean by mean free path? We have already discussed that as the postulates of kinetic theory of gases. Gas contains tiny rigid identical particles, and these particles are in random motion, and during their motion they collide with each other. So what is the distance travelled by a single particle between two successive collisions? That distance is called mean free path. And we can say that that is the distance travelled by a particle in a gaseous system without making any collision. That means it made a collision, and till the next collision, what is the distance travelled by it? Making a collision, between the next collision, what distance it can travel which is free from collision? That is mean free path. And here we are going to derive an equation for that mean free path. For that, we are considering that a gaseous system is there, and this gaseous system is traveling through a length, a container with a length L, and the particles are moving with an average velocity v. Suppose particles are moving with an average velocity v. For a time t, they can travel a distance s is equal to v into t. You can just take it as velocity into time. Okay. And you consider the particles are having the diameter 2d. Diameter 2d. That means radius d. So when you consider a particle of radius d, and when it makes collision with another particle, the centers of both these particles are at a distance 2d. Centers of these two particles will be at a distance of 2d. Okay? And you can consider this as a equivalent molecule of radius or diameter 2d. Okay, you can consider that as a equivalent molecule of diameter 2d at the time of collision. See, since the particles are very tiny, and we are considering that at the time this equivalent molecule is only traveling and all other target molecules are at rest. We are considering that in the gaseous system only this equivalent molecule is traveling one, and all other target atoms or target molecules are at rest. Okay? So we can say that when it travels, it can derive an area. When suppose this particle is traveling with a velocity v during a time t, the distance travelled by this particle will be v into t. And what is the cross-sectional area? That is radius is d, and the cross-sectional area will be cross-sectional area A, and A is equal to pi d square pi r square. Okay, so when this molecule is traveling with a velocity v during a time t, this much volume it can derive. What is the volume there? That is a cylindrical volume of radius, of area pi d square and length Vt. So the volume is equal to pi d square into Vt. Pi d square into Vt. Suppose per unit volume small n number of molecules are there. Per unit volume small n number of molecules are there. So within this volume how many particles will be there? How many particles will be there? The number of particles. Number of particles will be n into pi d square into Vt. N into pi d square into Vt will be the total number of particles present in that particular volume. So the distance, total distance traveled will be Vt. Total distance traveled is Vt, and within that distance how many particles will be there? N into pi d square Vt, pi d square Vt into n number of particles will be there. So actually what happens is total distance divided by total number of particles. That will give you the distance which is vacant of particles. Actually that will be the distance through which a particle can travel, a molecule can travel without making any another collision, because this is total distance divided by total number of particles. That will provide you the space where the particles are absent. So when the molecule is traveling through that distance, it will not make any collision because it is free from particles. So that will be Vt divided by pi d square Vt multiplied by n. Okay, so that will be the total distance or the total space which is free from collisions. Okay, so the mean free path will be Vt, and Vt that cancels 1 by n pi d square. 1 by n pi d square is the mean free path, and it is taking as lambda. Lambda is equal to 1 by pi n d square is the mean free path, which is the distance traveled by a molecule within a gaseous system without making any collisions. Here you remember, while we are saying, deriving this equation, we have said that only this molecule is traveling and all other target particles are at rest. So actually it is not so. All the particles are in motion. So when you are considering the movement of all the particles there, then here when you are calculating the distance between velocity between two particles which are colliding, there you have to say that it is the relative velocity between those two particles. So when you are having two particles moving with it is not there in the syllabus, but remember it is not in the syllabus, but remember that suppose V1 and V2 are velocities of two particles which are colliding, then the relative velocity between them will be V1 minus V2. So the magnitude of magnitude of this relative velocity V1 minus V2 will be, this is the relative velocity. So V relative will be root of V1 minus V2 dot V1 minus V2. That is the method of finding out the magnitude of a vector. So when you are calculating, this will be V1 plus V1. V1 plus V2, and V1 and V2 both are same. So we can say that it is root 2 V. It will be root 2 V. Because we have said that average velocity of all the particles in the gaseous system is same. So we can say that when you are taking this average velocity, that you have to replace by root 2 V. that you have to replace by root 2v. So this equation will become root 2 times 1 by pi mv square. So lambda will become 1 by root 2 pi n d square. So this is the mean free path when you consider all the particles are in the state of motion. Otherwise, if you are saying that only these two particles, except the particle molecule with the radius 2d, and all other particles are at rest, then the mean free path will be pi m d square. If all the we consider all the particles are under motion, that is 1 by root 2 pi n d square. Again, using the our ideal gas equation, PV is equal to NKT. When you are taking the 1 mole of a gas, it contains n number of particles, so PV is equal to NKT. So PV is equal to NKT. We can say N by V is equal to P by KT. What is N? Total number of particles, and this is per volume. So that will be equal to small n. Total number of particles per unit volume is small n. So this equation will become 1 by root 2 into pi d square multiplied by n. N is P, then KT will go up. So KT by root 2 pi d square P. KT by root 2 pi d square P is mean free path in terms of pressure, temperature and Boltzmann constant. What is D? D is the average diameter of the particle. Okay, so that is the concept of our mean free path. So mean free path is the distance travelled by a particle between two successive collisions, and its expression is given as 1 by n pi d square or 1 by root 2 pi n d square in terms of kT divided by root 2 pi d square. And the last content in this chapter, that is thermodynamics, is Avogadro number. It is very familiar what is Avogadro number and what is the significance of Avogadro number. So what is Avogadro number? The number of particles present in 1 mole of substance, that is Avogadro number. So when you are having a gas with a molecular mass m, so m gram of that substance contain Avogadro number of particles. So 1 mole means number of m gram of 1 mole of gas contains n number of particles. So in reverse we can say that if you are calculating the mass of n number of particles of that particular gas, it will be equal to its molecular mass. So 1 mole means molecular mass gram of that substance. It contains n number of particles, and it is independent of it is independent of the gas. Means if any gas you are taking, its molecular mass gram, it contains n number of particles. Suppose you are, for example, a gas A is there. Gas A is there, and its molecular mass is Ma. And for one particle, one molecule, its mass is Ma. What is the difference between these two? This is molecular mass. That means n number of particles have the mass Ma, and Ma is mass of one particle. And when you consider carbon, its molecular mass is 12, and the mass of one carbon atom will be Mc. Okay, so we can say that Ma proportional to Ma. Is it? As the any gas, its single molecule's mass is more, then this molecular mass is also more. So 12 proportional to Mc. Okay. So Ma by Ma equal to 12 by Mc. Ma is equal to 12 by Mc. So what is Ma by Ma? This is the molecular mass. This is mass of one particle. So ma divided by ma will be total number of particles in m gram of that substance. What is that? That is n. So n is equal to 12 by mc. Mass of one carbon 12 atom will be, mass of one carbon 12 atom will be 1.99265 into 10 to the power minus 23 gram. 1.99265 into 10 to the power minus 23 gram. So when you are dividing 12 divided by 1.99265 into 10 to the power minus 23 gram, you will get the value of n. And what is that? Value of n will be 6.023 into 10 to the power 23. 6.023 into 10 to the power 23 number of particles. Okay, so it is independent of Ma. Means 12 and mc, 12 is constant, mc is also constant. So it is independent of Ma. That means if you are taking any gas, if you are taking any gas, if you are having the molecular mass of that gaseous substance, it contains Avogadro number of particles. It contains Avogadro number of particles. Okay, so that is the importance of Avogadro number. Okay, and what are the significance of Avogadro? If you know the gram atomic weight, if you knowing the gram atomic weight of a substance or element, then if you are dividing that with the Avogadro number, you can find out the atomic mass. That means atomic mass multiplied by n should be our molecular mass. Okay, then atomic mass of an element can be calculated by knowing the gram atomic weight divided by Avogadro number. Then molecular mass of a compound, again molecular mass divided by Avogadro number will provide you the mass of the one molecule. Mass of one molecule will be molecular mass of the molecule divided by, molecular mass means mass of one mole of substance. If you divide by total number of particles, what is the total number of particles? Avogadro number of particles. Very simple logic. Okay, then number of atoms in a given mass of an element. Again the same concept. That means you can find out the number of particles or mass of one atom or molecule if you know the gram atomic weight. That is, or gram molecular weight. That is the significance of Avogadro number. Okay, so that's end of this chapter, kinetic theory of gases, behavior of perfect gas and kinetic theory of gases. So we have started with the heat transfer. And we have seen heat transfer, then thermodynamics, first law of thermodynamics, second law of thermodynamics, then heat engine and refrigerator as an example for different statements for the second law of thermodynamics. Then we have seen isothermal process and adiabatic process separately. Then behavior of a perfect gas. All these are coming under the same concept of thermodynamics. So this is the end of the thermodynamics, and during the next class we will start with the last unit in your syllabus, that is waves and oscillations. Okay, before that you just refresh through the concept of wave and oscillation that you have already learned from your lower classes. Then it will be easy for you. Okay, so we will meet in the next class. Till then, bye.